in every cusp. So for SL2, this just means, so we have every function on this quotient has a Fourier expansion in this cusp, and the constant term has to be 0. And this cuspal part is quite nice because it somehow, in certain ways, it is very similar to the case that the quotient, to the case that the manifold is compact, and the analysis of this space is much easier than of all of this. But also, it's quite important because the L2 space has a direct decomposition as the cuspal part plus the constant. So this is just a constant function plus something which is related to the theory of Eisenstein series. And this is of course well understood, but this is also well understood if you know how the cuspal functions for lower dimensional, for groups of lower rank behave. So what's really important is to understand this cuspal part. And we want to consider certain operators on the space. First of all, we have, so for NS2, there's this very important operator, namely the hyperbolic Laplacian. And in higher dimensions, we have something similar, namely, this is just the algebra of left SLN are invariant differential operators. Or if you want, the center of the universal enveloping algebra. For SLNR. And for NS2, this is really nothing else than the algebra spanned by the Laplace operator. And this algebra D acts on the cuspal part, and these functions are this part of the L2 spectrum is really nice because it actually decomposes discretely under this action. So we can find a basis for L2 cusp consisting of simultaneous eigenfunctions for delta. And we say that F is a mass form if F is an eigenfunction for D. So for NS2, these are just the usual mass forms which you've probably seen before. And so if F is such a mass form, this just means that we can associate an eigencharacter to F on D, which is usually called the infinitesimal character of F. And for NS2, lambda F is just corresponds to the Laplace eigenvalue of F. And we we view lambda f actually as an element in Cn modulo the Weyl group for SLN. So I write W for the Weyl group, which is just the symmetric group on n symbols. And we embed Cn minus 1 into Cn by taking n tuples whose sum is 0. Yeah. So this is isomorphic to D star by Parashandra. But for SLN, this can be seen more directly. So we view lambda f really as as an element in C to the n minus 1. So first of all, it would be good to know that this is not empty, this set of mass forms. So I want to speak about them. So this is in our case indeed true. So we have the Weyl law, which tells us that the number of f mass forms whose eigenvalue is bounded by some t is asymptotic to some constant times t to the d, where d is the dimension of Hn. So for n is 2, this is classical result due to Selberg. For n is 3, this was proved by Miller. And for general n by Müller and also Lindenstrauss and Venkatesh, who did this in more generality. But this is in general not a trivial result, and if you deform your lattice gamma slightly, then probably there are no mass forms.
Sorry, in the case of SL2,
yeah.
where are the automorphic modular forms in this case?
Yeah, these are in general not holomorphic, so I should say. Yeah, so if you would have to consider different k types, and then they show up, but yeah.
Does Weyl have anything to do with Weyl's law?
Sorry, what? This is Weyl's law.
But Weyl is not in the list.
Yeah, he did it for Riemann.
Actually, I think it was like this guy introduced himself to Hilbert and the crew. I mean, he was a student. Hilbert said this would never be done.
Okay. Okay, so in any case, so we have this algebra of differential operators acting on the cusp forms, but we actually want to consider another algebra of operators also acting on the cusp forms, and these are the Hecke operators. So if we have a rational matrix of positive determinant, we can consider the double coset gamma, small little gamma, which can be written as a disjoint union of left cosets for suitable delta j in GLNQ. And we introduce the Hecke operator T gamma f with f in the cusp form by defining this as the sum over f of delta j g. So since f is left gamma invariant, this is well defined. And we denote by H the algebra under convolution, so the C algebra under convolution of all T gamma. And actually this is the same. So for GLN this can be seen by the elementary divisor theorem, for example, as the C algebra generated by all gamma, where gamma is some diagonal matrix. Such that the quotients are integers. And it's usually easier to just consider operators where those mi's are just powers of some fixed prime number, and this is enough in general. So this is actually the same as the product of all HPs for P prime, that this HP is generated by T gammas with gamma just a diagonal matrix. P to the lambda n, lambda I, z. And we say that F is a Hecke-Maass form. So if it's first of all a mass form, but if F is an eigenfunction for D and also H. And one should note that the Hecke operators, H and the differential operators, they commute with each other. So they commute pairwise. So we can indeed find a basis for the cuspal forms consisting of Hecke-Maass forms. So we can find so as before, so F being a mass form had the consequence that we had the infinitesimal character from the algebra of differential operators to C. And when F is an eigenfunction for all Hecke operators, we can then, of course, also associate a character on HP. So F, a Hecke-Maass form, can associate a character from HP to C, which is called the Sarnak parameter. And so A f of P, and can be represented as a tuple of n complex numbers. Whose product is 1. And the evaluation at the Hecke algebra is given as follows. So by the Sarnak isomorphism, the Hecke algebra is actually just a ring of Laurent polynomials, which are symmetric under the group Sn. And then if the Hecke operator T in HP corresponds to the symmetric polynomial, then AFT, the eigenvalue of F at T, is given by phi of AFT. So, for example, for NS2, you get just the usual picture that HP is generated by the Hecke operator TP corresponding to the double coset gamma P1 gamma. And phi, which corresponds to this, evaluated at Sarnak parameter F1P. So this is just the inverse, just the sum of those two things. So we are interested, as the title of my talk said, in the distribution of Hecke eigenvalues, and it's a little better not to. So it depends on the formulation, but sometimes it's better to not look at the distribution of the Hecke eigenvalues, but the distribution of the Sarnak parameters. So but to talk about the distribution of something, we have to say with respect to what measures, and denote by mu infinity the spherical Poincare measure for SL and R. And this lives on the space C n-1 mod W, which I introduced earlier. And let me denote this in the following by A star C mod W. And for every prime P, we have the spherical Poincare measure on SL and QP, which lives on C star to the n mod W. So in principle, mod C star. And yeah, so the Sarnak parameter is an element in C star to the n up to the action of the Weyl group. And these measures are actually supported on much smaller sets. So mu infinity is supported. So mu infinity and mu p are both only supported on the tempered representations. So these are just the unitary duals of those groups. And the Poincare measures are supported on the tempered representations, which corresponds, in this case, to the imaginary axis, so to speak, so IA star mod W. And this is basically the same, and supported on C1. And actually the generalized Ramanujan conjecture says that this should actually, so that lambda f should be tempered, corresponds to a tempered representation, as well as every Sarnak parameter. For all Hecke-Maass forms, F and for all primes P. So, and the question now is, what can we say about the distribution of the lambda f's and the AFPs in these spaces? So, with respect to the Planck measures. So, how are the lambda f and the AFP distributed in with respect to mu infinity and mu p. So the first case one can look at are the infinitesimal characters at infinity, so the eigenvalues under the differential operators. And there one has a refined Weyl law, which is due to Laplace and Miller. Which says the following. So we fix some subset omega in the tempered dual and consider the following family of Maass forms. So we put f of t to be the set of all Hecke-Maass forms f with infinitesimal character lying in t times omega. For t, just a parameter, just a positive real parameter. Yeah. And from now on I only consider even Hecke-Maass forms. So this even, you shouldn't worry too much about this even, but when I later want to translate to the idyllic picture, it's a little bit easier to consider only even things. So, for example, if n is 2, even just means, so f is even if it's invariant under some involution, namely under f of minus z bar, the same as f of z. So here in this picture, you have the involution reflecting over this axis of symmetry of a real part z is 0, and even forms are just those which are invariant under this involution. And then Laplace and Müller prove the following. Namely that this set, the size of the set is given by the volume Hn mod gamma over the size of the Weyl group times an integral against the Planck measure. So we have t omega d mu infinity. And they also gave an upper bound for the error term, so it's t to the d minus 1 times some log terms. And moreover, they could also show, so by definition of this family only counts mass forms which satisfy the Ramanujan conjecture. So maybe you're missing many of the forms which violate this conjecture, but in fact they also showed that the number of f with infinitesimal character less than t, for which so the infinitesimal character is not unitary. This is actually, there are much fewer than than all of the Hecke-Maass forms. So this is some kind of bound towards the Archimedean Ramanujan conjecture on average. So I'm cheating a little bit here because due to technical reasons, Lapine and Müller only considered, so they didn't consider the full modular group gamma as SL and Z, but just congruent subgroups of level at least 3. But so actually this theorem basically will follow from the next theorem I'm going to write down. So this is actually true. So this is the following theorem, just due to myself and Nicolas Templier. So you now not only want to consider the infinitesimal character at infinity, but now also want to understand how the Sarnak parameters at finite primes are distributed. And we can show the following. So there exist constants C1, C2, and eta, such that for all symmetric polynomials phi, so basically for all Hecke operators, and all primes p, we have the following. So the first thing is that this is yeah, what I already wrote down basically. So the volume of Hn mod gamma times the volume of T omega plus some upper bound for the error term, which is now worse than what Lapine and Müller had. So yeah, I should probably say that SL and Z has to be replaced by congruent subgroup. Of level at least 3. The eta is independent, so it depends only on n. So yeah, yeah, n is fixed for everything. So, but if you want, I can. I mean, I'm not sure. Perhaps that's independent, but I will claim this. So maybe you can say something about it. Yeah, probably it depends on it. No, it depends on it a little bit at least. So, and the second part is that if you consider the sum over elements in this family f of t and evaluate this polynomial at the Sarnak parameter of f. So this is just a Hecke eigenvalue, so to speak. And you normalize this by the number of elements in your family. Then the limit as this goes to, as t goes to infinity, is equal to phi integrated with respect to the Cauchy-Weyl measure at p. And we can give an upper bound for the error term. So this is bounded by c1 times p to the c2 times the degree of phi times t to the d minus eta for all t at least 1. Yeah, and c1 and c2 also depend again on n. So okay, so let me say a few remarks about this. So similar results can be proved if you replace gamma, so if you replace SLNZ by some congruent subgroup. And also if you replace SLNR by SLNC, and the hyperbolic n space by SUN. And instead of SLNZ, you can consider gamma the SLNOF for f some. So OF, the ring of integers of some imaginary quadratic number field. So there are similar results for this situation, and for small n, there were of course similar results available before. So for n is 2, this situation was studied by Sarnak, and for n is 2, this situation in the complex case was studied by Imamoglu Drauf, and for n is 3. Blomar and his collaborators also have some results in this direction. But for higher rank, it becomes increasingly difficult. So let me tell you a little bit about consequences of this result. So first of all, we can give a bound towards the Ramanujan conjecture at P on average. So more precisely, can say the following. So corollary, there exist constants c and omega such that for all primes and for all parameters theta greater than 0, we have that the number of Hecke-Maass forms, so the number of f in f of t, for which the maximal value of the Sarnak parameter, so the entries in the Sarnak parameter, is at least theta. This is bounded by t to the d minus c times theta plus omega over. And this implied constant depends on n, p, and theta. Okay, so one should probably remark that the left-hand side is 0 if theta is at least 1/2 minus 1 over n squared plus 1, which is due to some result of Logarithmic-Sarnak. And yeah, for n is 2, a similar bound with slightly better exponent was proven by Sarnak, and for n it's 3, something related was proven by Loma and his collaborators. So for general n, this was not known before. So, but you see, this only becomes meaningful if p is large compared to theta to the -1. So the other consequence following. Namely to the distribution of low-lying zeros of families of L functions. So if we have such a Hecke-Maass from F, we can associate to this a standard L function, for example, L of SF, which for real part S very large is just the product over local L functions. And this LPSF can be actually defined as in terms of the Sarnak parameters, so it's the determinant of the n by n matrix of 1 minus Sarnak parameter times p to the minus s over -1, and we view the Sarnak parameter as an element in SLN C, just as a diagonal matrix. So, and more generally, one can consider more general representations you can consider representations of the L group of PGLN, which is just SLN C. So this is a space where the Sarnak parameters live, to some GL of some vector space V. And you can consider L functions L of S F rho, which again for real part S large can be defined in terms of the Sarnak parameter and rho as the determinant 1 minus rho of AFP. But in general, so for LSF, you know that this function can be continued to to S in the whole complex plane, and to a meromorphic function. But in general, you don't know that this can be continued, and there are analytic difficulties. So we can consider only very few rows. But so. For every rho, this FT therefore defines, so to speak, some family of L functions, which I denote by F rho of T. And these have, so such families of L functions have recently been quite extensively studied by Sarnak, and Templier, for example. And yeah. So in general, one expects that these L functions satisfy the analog of the Riemann hypothesis, so that the zeros of those L functions only lie on the axis of real part s is 1/2. And so say if we know that for some rho this L function has a continuation to all of C, we can of course define the zeros of the L functions. So suppose the automorphic continuation we write rho just 1/2 plus I gamma fj for the zeros of L as f rho. J runs through the integers, and this gamma f j is a complex number, so we don't assume the Riemann hypothesis, but in general they are expected to be just real numbers. And the question now is to understand how these numbers gamma f distribute around the expected point of symmetry, so around 1/2. And the density conjecture for, I only stated for level 1, says the following, namely that for every Schwarz function phi on R, the limit of the sum over forms in the family F and Z and Z phi so the limit of this should exist and so as t goes to infinity, and it should be equal to the integral over R phi x w of x for w a certain density associated to the symmetry type of the family F-O. And this symmetry type is connected to the theory of random matrices.
Remind me what C rho of that is.
Oh, I'm sorry. Yeah, so C rho, I don't want to define it, but C rho of F is the analytic conductor of LSFO. And so I don't want to define it, but if rho is just a standard representation, then this is about the size of the norm of the infinitesimal character to n, to the n. So something like this. And the consequence of our theorem, the following. If rho is either the standard representation or the symmetric square or the exterior square or the adjoint representation, then for every phi such that its Fourier transform phi hat has sufficiently small support, the limit of star exists. And if n is at least 3, it equals, so we can write down just the integral over phi of x. If rho is the standard representation or the symmetric square or the exterior square, and the integral over phi of x times 1 minus if rho is the adjoint representation. 2 times.
So this is a part of your theorem?
Yes. Okay, so for, I mean, you see, it's not the full conjecture because we have to assume that phi has sufficiently small support, and the size of the support is actually related to our error term. So we could bound the error term, and the better the error term, the better, so the larger the support of phi hat is allowed to be. But so it's of some interest to make this error term as small as possible, or at least to make the constants in this error term more explicit. Okay, so the last 8 minutes, I want at least tell you a little bit about the idea of the proof and why I mentioned the Selberg trace formula in the title of my talk. So of the theorem. So to state the proof, or the idea of the proof, I have to translate to the idyllic language. So to give you a brief dictionary.
I guess that's because somebody wrote the trace formula.
Yes, I mean if you want to write it down in.
Selberg,
Of course, the Selberg trace formula is. In general, it's much more convenient to work over the idea. So.
I'm just joking, but I think maybe you should highlight, and you will, that Arthur doesn't even know that his formula converges absolutely. So to do any kind of analysis,
Yeah, you have to be very careful.
You can't derive it from his knowledge that he gets to collect. So he's amazing that he can compare different formulas. But if you actually want to put it, use it directly, it's very hard.
Sure. So first of all, our main objects, namely the even mass Hecke-Maass forms, are the cuspal representations on GA, GQ there. So G is now GLN, which are invariant under a maximal compact subgroup K. So K denotes O of n times SL and Z hat. This is a maximal compact subgroup in GLNA. So A is the ring of ideals of Q. And the even Hecke-Maass cusp forms are in the adelic representation theoretic language just the spherical unramified representations of GA with a trivial central character. And Arthur's space formula in its most abstract forms, just an identity of distributions of some geometric side and some spectral side on some space of test functions H, which are usually compactly supported. And the strategy now is identify the sum phi of AF pi AFP with the main term of the spectral side for a certain test function, which I denote by f mu infinity times t times some characteristic function of some maximal compact subgroup outside of P and infinity. And t is the Hecke operator corresponding to phi. And this is not completely true because I actually don't want to have the main term of the spectral side, but the main term of the spectral side integrated over t times omega. And this is why I have a spectral parameter at mu here. And I don't want to say anything more about the spectral side, actually. But I want to say a few words about the geometric side, which was much more work for us. So one has the spectral side, and of course one has to to analyze the geometric side to make any sense of this. So one has to find the main term in this now also, and prove that so JF and prove that the rest only contributes to the error term. Okay, so I don't really have time to say anything more. So let me just say that this geometric side has a fine expansion, Arthur's fine expansion, over Levy subgroups M and elements gamma in MQ up to conjugacy of certain global coefficients A, M, gamma, S, and weighted orbital integrals A, J, M, gamma, J, M, G, which depend on gamma and F, mu, and T. So, and the problem now is that so S is a finite set of places, and we want to vary this T and we want to vary P. The main term on the geometric side is just the term which corresponds to M equals the group G and gamma in the center. But we have to then show that all the remaining terms only contribute to the error term and bound this error term quantitatively. And the problem now is that so the first problem is these global coefficients are in general not really understood. So one first has to prove some upper bound for these things, independence of gamma and S, since gamma and S will vary as we vary T and our prime P. And then we have to do basically the same for the weighted orbital integrals, where one has to basically bound Archimedean weighted orbital integrals, which are related to to certain estimates on spherical functions which come out from our construction of F mu infinity, and also some p-adic orbital integrals which are related to the Hecke operators. Okay, so I